All right, so what did you guys get when you put in 2? Okay, 0 over 0. So if you put it in the numerator and then put it in the denominator, you got 0 over 0. So if you guys will do that for me, if you didn't do it, just draw like a little arrow and say that you got 0 over 0. That is a significant thing. So on these problems, when you do direct substitution, you get 0 over 0. Most of the time, the limit exists. And it exists somewhere where there's a hole in the graph. Not always, but most of the time, when you get 0 over 0, it exists. Now, somebody had that equals 0. 0 over 0 does not equal 0. 0 over 0 does not equal 1. It's an undefined value. It's indeterminate, actually. It doesn't really have a value. Okay, and so what happened on the table at x equals 2? There is an error. All right, and as you approached 2 from both sides, what did the graph get closer and closer and closer to ish? So what that means is there's actually a hole in the graph there. But when you're looking at the calculator I don't think has pixels to be able to show holes in a graph. So you just have to trust your own understanding to figure that out. Okay, and then we factored the function. And those will cancel out because you have an x minus 2 in the numerator and in the denominator. And then what did you get when you plugged in 2? So that was a really good guess, that 1.25. That's exactly what it is. So you guys didn't realize it. When you were last year doing rational functions and finding holes in the graph, you were actually doing limits. Just didn't have the notation that went along with it. So what about the other one? If we're finding the limit as x approaches -2, and I can use this reduced version, and I put in -2, this time you get 1 over 0, and 1 over 0 means that the limit is not going to exist no matter what. And can you look at the graph and tell the limit doesn't exist there? Because there's a vertical asymptote. So the reason it's different is because the limit does not exist. Right, so that's a pretty good rule of thumb. If you're doing direct substitution and you get something like 1 over 0 or -5 over 0, then the limit is not going to exist. But if you get 0 over 0, it probably is going to exist. All right, so I have 2 days worth of notes we're about to hand out. We will not get through all this today. All right, so today we're going to focus on algebraic approaches. Now, there is definitely going to be 1 or 2 where you might have to use a graph to figure it out because there's not really an algebraic approach to it. But whenever you're evaluating limits, where you actually have the function. So the ones we've been focusing on is this part right here has just been f of x or g of x. And so we've always had to use the graph. But when that's an actual function, we can use algebraic approaches. And the first thing you always want to do is direct substitution. Because sometimes when you plug that value in, you just get a number like 8. And that's the value of the limit. So those are great. You don't have anything weird to do. You just do it. All right. Sometimes you're going to need to use a memorized form. Now, the reason on that packet, I don't know if you guys did, I think it was on this packet. I had you do several that were the absolute value of something over that same thing without the absolute value, because I want you to memorize what that graph looks like. And so if we have the absolute value of x over x, Or it could be x over the absolute value of x. What are the only two values you're going to get when you plug numbers in? There's only two numbers that you got. You got a horizontal line at both those numbers. Do you remember? 1 and -1. All right. And so if you're unsure of if when you plug this number in, you get 1 or -1, you can just pick a number and plug it in. This one in particular, is on the left side of 0. You would get -1, and then on the right side of 0, you would get -1. Now those can change. Like if you have an expression like 2 minus 1 or 2 minus x, and the absolute value of 2 minus x, the 1 and -1 are switched. So sometimes you want to plug in a number, but basically, whatever makes it get 0 over 0, you'll have the two open circles. And then on one side, you'll have -1. On the other side, you'll have 1. So that's the graph I want you to kind of have in your head. All right. Sometimes you need to do what you guys just did on the Lindsay Lohan activity, where you factor, simplify, and substitute. All right. Sometimes you're going to need to do some algebraic manipulation. So factoring, simplifying, and substituting, that's also algebraic manipulation. One thing we're going to do today is simplify complex fractions. That used to be a really heavily taught subject or topic in Algebra 2, and they kind of took it out. So you may or may not be super comfortable doing that, but we'll definitely practice it. All right. Sometimes you can't do something algebraically, and you have to look at the graph or table. All right, and then all the stuff underneath that, we're going to hold off and talk about tomorrow, some properties of limits. But we are going to do this little box over to the side. Okay, so if you do direct substitution and you get a number other than 1, and that number is greater than 0 over 0, then that technically means that part of the graph is going to go to infinity. If that number is not 0 and it's less than if it's a negative number, then that means that's going to go to negative infinity. Now, we're still just going to say it does not exist, but that's just a little heads up. All right, if you get 0 over 0 or infinity over infinity, which we haven't quite got there yet, those are considered to be indeterminate. Which means you're going to have to do something else to figure out what the limit is. And then do you guys know what you get if you take a number and divide it by infinity? If you take a number and divide it by the biggest number in the world, what do you think you would get? Something extremely small, like 0. Very good. All right. So we're going to skip all the way down to the example 1. All right, and the first thing we're going to do on all of these today is start off with direct substitution, where we just take this value here and you plug it in. And if you, as soon as you plug in that value, you stop writing limit. All right, so when I plug in the 3, I'm just going to drop off the limit, plug it in. I get the square root of 4, which is just 2. Those are the best. Okay, now the next one, you're going to have to remember some things about pre-calculus. Hopefully you will. So we're going to start with direct substitution, where I'm just going to take that 1 and I'm going to put it in for the x. And when I do, I'm going to get the cosine of 1 pi, or just the cosine of pi over 3. which is this finger. Is that what you're talking about?
Yeah, but then it's bottom over top.
Cosine is not bottom over
Bottom
top.
over 2, just 3 over 2.
Mm-mm.
Top over 2.
Top over 2. We probably need to review that sometime. I might post my video about doing that for you guys, just so you can remember. Those of you who weren't in my class probably don't have any idea what I'm talking about. But there is a way you can do a hand trick for these special angles where that's my thumb right there. All right, so this is 0, pi over 6, pi over 4, pi over 3, and pi over 2. It's an alien finger. All right, and so whatever you're finding the cosine of, you bend that finger down. And for cosine, it's going to be equal to the square root of the top fingers over 2. So in this case, I have one top finger, so that's going to be 1 over 2. For the sine, it's the square root of the bottom fingers over 2.
Bottom over top.
And tangent is square root of the bottom over square root of the top. Good. It's super messy. Maybe you can read it. Square root of the bottom over square root of the top. That's just a quick way. We didn't start off with it that way, but once we learned other ways to figure it out, we kind of learned that shortcut. Okay, so let's look at C on the back. Now when I plug in, that's not C. When I plug in -2 in the numerator, it's going to be 4 plus 16 minus, 4 plus 8 minus 12. What is that going to be? Whoa. All right, it's a perfect 0. And then in the denominator, it's going to be 0. So if you guys will do me a favor and never write that it equals 0 over 0, because that's not true. In a second, we are going to figure out what this limit equals, and it's just a regular old number. So you just draw this little arrow saying it yields 0 over 0, and 0 over 0 is indeterminate form. Which means you need to do something. And in this case, what we need to do is just factor and cancel and see what happens. Now, I'm going to teach you the right way to write all these limits. But it really only matters on free response, but I want you to practice writing it correctly. And so until you actually plug that -2 in and get the final answer, you need to keep writing the limit. I know it's going to be annoying. It should be okay. So we still have this limit, but we're going to go ahead and factor the numerator. Now, if I get indeterminate form, more than likely this x plus 2 is going to cancel, so I pretty much already know what one of my factors is. All right, so then I can cancel the x plus 2's. Now I can take that -2 and I can plug it in, and when I do that step, I quit writing the limit. So that's going to be -2 minus 6, which is -8. So that's the value of that limit. So that's why you don't say it equals 0 over 0, because it doesn't. It equals -8.
Can we factor out the sum? What is that?
That is the
The
factor simplify substitute, yes.
So what does the 0 over 0 mean? I don't get that.
Because there's a hole in the graph. So anytime, almost all the time, you get 0 over 0, there's a hole in the graph there. And the limit exists, so then you can find it. All right, let's look at the next one. So if I put in -2 and I cube it, that's going to be -8 plus 8 is 0. So I do it again. I get 0 over 0 again. So that means I need to do something. And that something is to factor. So that numerator is the sum of two cubes. Now, do you guys remember how to factor in sum of two cubes?
Can't you just do x plus 2?
Mm-mm. If you do x plus 2 cubed, you're going to get like 4 terms. You'll get x cubed plus 3x squared plus 3x plus 2. Not 3. Plus 6x plus 2. So, no. Actually, b plus 8. Anyway, no, you can't do it that way. It's a small set, a parentheses, and a large set. What goes in the small set?
X plus 2.
X plus 2. Nice.
X squared plus 4.
Plus minus 4x. Nope, just kidding. 2x plus 4. Right, so what you do is you find each cube root and you bring it down with the sign. That's a small set. And then square the first one, change the sign, multiply them together, square the second one. All right, and then you notice that the x plus 2's will cancel. So now I can go ahead and substitute. Four plus 4 is 12. Yes, okay? All right. This next one is the one I was kind of talking about that you might not have a lot of experience dealing with these. This is what a complex fraction is when you have a fraction inside of a fraction. This is one you guys actually did using a table. I pulled it off your homework from the other day. And so sometimes you can do ones like this using the table, but a lot of times limits are on problems where you can't use a calculator at all. So it's okay. We are going to simplify this complex fraction by getting rid of all the little denominators. Now, if you were in my class, I talked about this before. This one is just more difficult than ones we've done before. So it's okay. We are going to multiply by some things to get rid of the little denominators. So what are those things going to be? X plus 1 and 4. And it's only legal if you do that in the numerator and in the denominator. So if that's kind of confusing for you, we'll write a note. So multiply by all the little denominators. Now, in the denominator, there's so many denominators. So in the big denominator, we're not going to distribute that. We're just going to leave it separate in factored form because more than likely that x minus 3 is going to cancel out. It's just going to make it easier if we don't multiply it together. Because if we did, then we'd have to factor it again, and that would just be counterproductive. All right, so this is going to be the limit as x approaches 3. All right, when I multiply x plus 1 times 1 over x plus 1, they're going to cancel out. And then what is that going to leave you with? Close. There's one more thing that we're multiplying by. 4. Good. Right, minus. Now, if there's a minus, I'm just going to go ahead and do a set of parentheses because that's easy to make a mistake. All right, and then this time when I multiply these, the 4's cancel out, but there's still going to be this x plus 1 times that 1. Oh, one thing I didn't do that we should have is said that this yields 0 over 0. Sorry. Okay. So, because I'm not quite ready to plug in the 3, I'm going to keep writing the limit. I'm going to go ahead and distribute that negative and combine the like terms. Okay, so they are minus or negative x plus 3 and x minus 3 are not the same, so they can't really cancel. What can you do though? Can you make them the same?
Where did the 3 come from on the top?
Oh, yes.
The 4.
That's 4, and then that's minus 1.
Oh,
I kind of skipped steps. So can I make them the same? Is there something I can do to negative x plus 3 and make
Distributed.
factor out a negative? Yeah. All right, we're running out of room. It's okay, we're almost done. Okay, so now these x minus 3's can cancel, and then I can plug in 3. And that is going to be negative 160, which is what you should have got something close to that. You probably had to give a decimal version of it when you were doing the table, but that is what the limit is equal to. Okay, so we're just going to do one more example today and save the rest of those guys for tomorrow. And so F is like one of those forms I want you to have memorized, or a graph I want you to have memorized. And so I'm just going to do a little, when I do plug in 2, we are going to get 0 over 0. And so wherever this graph gives you a 0 over 0, which is at 2, that's where you're going to have 2 open circles at 1 and negative 1. And then we just have to figure out if the tail coming from the left is at negative 1, or if the tail coming from the right is at negative 1. And so to do that, bless you. To do that, you can just plug in 0. 0 is on the left side of 2. If I make both of these 0, the absolute value of negative 2 is 2 over negative 2. That's negative 1. So that means that over here, you'll have it at negative 1, and then the other side will be a positive 1.
Redo that last.
Okay, so if you just don't know if it's positive or negative 1. If I take something on the left side of 2, which was 0, and I plugged it in, on the numerator it's the absolute value of negative 2 over negative 2. So that's 2 over negative 2, which is negative 1. So everywhere over here is going to be negative 1. And if you're still not sure, if you don't trust yourself, plug in 3. And when you plug in 3, you get positive 1. Okay, so this question is, which is the limit as x approaches 2 from the right side. So as we're approaching from the right, where am I on the graph? At 1 or at negative? Or at 1? What if that plus wasn't there? What if it was just the limit as x approaches? It would be, does not exist. Very good. All right, any questions? Okay. Your assignment is out of the book, and I went ahead and just put a bunch of books up there. Anytime you're in class and you want to use a book, you can. These are pretty randomish numbers.
Do we need our own piece of paper for that?
Yes.
We're supposed to send in our stamp sheet with that packet.
No, it's a grade, so you don't have to.